안녕하세요. 4차 산업혁명 기획 3주 1차 시강의를 시작하겠습니다. 지금까지는 책의 순서대로 1장, 2장을 차례로 강의했습니다. 그런데 3, 4, 5장은 다른 장을 강의할 때 포함해서 강의하는 것이 더 효과적이라고 판단됩니다. 따라서 저희는 IT 기술과 관련이 깊은 6장부터 교재는 5장입니다. 다시 순서대로 강의하도록 하겠습니다. 6장은 New Computing Technology로 새로운 컴퓨팅 기술을 다루도록 하겠습니다. 먼저 Moore's Law, 무어의 법칙에 대해서 알아보겠습니다. Moore's Law는 반도체 직접 회로의 성능이 24개월마다 2배로 증가한다는 법칙입니다. 경험적 관찰의 바탕을 두고 있고 인텔의 공동 설립자인 고든 무어가 1965년에 내놓은 것입니다. 지난 60년간 반도체는 무어스 로만큼은 아니지만 엄청나게 빨라지고 가격은 내려갔습니다. 그러나 반도체 소재인 게이트도 아무리 작아도 분자보다 작아질 수 없다는 물리적 한계를 갖고 있습니다. 그렇다면 무어스 로 다음에는 무엇이 있을까요? 존 헤네스의 강의를 통해서 알아보겠습니다.
I'm delighted to be here at Zeitgeist and talk to you about what is one of the most fascinating and monumental times in the entire history of the computer industry.
컴퓨터 역사에서 가장 기념비적인 지금 이 순간에 대해서 말씀드리겠습니다.
And that's the coming together of two eras, a change that's absolutely phenomenal. The end of Moore's Law.
지금 두 시대가 만나고 있습니다. 하나는 무어스 로가 끝났다는 것입니다.
And the beginning of the AI era. And we stand right at that junction.
또 하나는 AI 시대가 이제 시작됐다는 것입니다. 우리는 그 정션에 있습니다.
Moore's Law, first of all, it is not a law. It is not a law. It was a prediction by Gordon Moore, made originally in 65 and then modified in 1975, that the number of devices we'd have on a chip would double every 2 years.
무어의 법칙은 칩 위의 디바이스 숫자가 2년마다 2배씩 증가한다는 것입니다.
But that prediction became reality. The industry stretched and tried to develop it.
그런데 산업은 크게 성장했고 그의 예언은 현실이 됐습니다.
Pull this cell phone out of your pocket. It has more memory than all the memory made for every computer in the world in 1970.
여러분 휴대폰에 있는 메모리가 1970년대 모든 컴퓨터에 있는 메모리보다 큽니다.
And you buy it for 1/1,000th the cost of one computer at that time.
그리고 지금은 그때 컴퓨터 가격의 100만 분의 1로 메모리를 살 수 있습니다.
So it's a phenomenal change, but it's coming to an end. And you can see it on this curve here. We've begun to deviate. In fact, we're now about a factor of 15 off of Gordon Moore's original prediction.
그런데 고든 무어의 법칙은 이제 끝나가고 있습니다. 이제는 팩터 15만큼 현실과 차이가 납니다.
Of course, Gordon said this. All exponentials have to come to an end. By definition, they have to come to an end.
물론 고든도 그런 기하급수적 성장은 언젠가는 끝나야 된다고 말합니다.
Well, what have we done with all that amazing computer power? We turned it into faster computers. That's what we really did with it. And if you look at the speed at which computers have accelerated since the 1980s, it's amazing. If automobiles made the same progress, you would drive across the country in 2 minutes. And by the way, when you arrived in New York or Washington, you'd pack your car up into something a little bigger than a cell phone and stick it in your pocket, and you wouldn't have to pay for parking in New York City. Very important.
발표자가 설명하고 있는 그래프는 지난 40년 동안에 마이크로 프로세서가 얼마나 빨리 빨라졌는가를 나타내고 있습니다.
Well, what's happened with all that computer power? We all use computer. How many people think their computer is too fast? How many think it's too slow? Yes, of course.
그런데 그 빨라진 컴퓨팅 파워가 다 어디로 간 걸까요?
What have we done with all that computer power? Well, the first thing is we built lots of new capability with it. We built the World Wide Web. We built programs like Google Search. We built things that do things for us, including, by the way, automatically answer emails if you want it.
우리는 그런 성능의 발전으로 컴퓨터의 기능을 발전시켰습니다. 예를 들면 월드 와이드 웹, 구글 서치, 자동 이메일 같은 것들이죠.
But we did something else. We liberated programmers. We developed programming languages and systems for them that would increase the productivity of programmers.
그런데 정말 중요한 것이 더 있습니다. 바로 프로그래머의 생산성을 향상시킨 것입니다.
So that they could write more software. How did we do it? We gave them hardware that was cheap and free. So they didn't have to worry about how fast the program ran.
프로그래머들이 빠르고 싼 컴퓨터를 가지게 되면서 일단 속도 걱정을 덜하게 됐습니다.
This is a great curve out of a paper from some colleagues at MIT. So they start with a program, matrix multiply. You all remember matrix multiply maybe from high school?
다음은 MIT에서 나온 훌륭한 페이퍼입니다. 매트릭스 멀티플리케이션 경우에 어떤 소프트웨어 랭귀지를 가지고 프로그램을 짜느냐에 따라서 63,000배까지 차이가 날 수 있다는 것을 보여주고 있습니다.
They wrote a version of this in Python. Python is the programming language that many courses teach programmers for their first language. It's what many people on the web use. It's an incredibly powerful programming language.
첫 번째 프로그램은 아주 강력한 프로그래밍 언어인 파이썬으로 짰습니다.
They wrote it in Python. Then they rewrote it in C. C is what things like Windows and Linux are written in. It ran 50 times faster.
그 다음에는 C로 프로그램을 짰습니다. 윈도우나 리눅스를 만들 때 사용된 언어죠. 무려 50배나 성능 향상이 있었습니다.
Just by rewriting. Then they took advantage of parallelism that exists in the machine and they optimized the memory behavior. And they took advantage of some special instructions that are inside an Intel processor.
다음 단계로는 메모리 옵티마이제이션을 하고 인텔 하드웨어에 있는 싱글 인스트럭션 멀티플 데이터, 패러렐리즘, 병렬성을 활용해서 더욱 가속을 했습니다.
Final program ran 63,000 times faster.
그 결과 63,000배의 속도 향상을 얻었습니다.
So what does this all mean? It's coming to an end. Are we going to have computers in the future? Well, we're certainly investing in research. It is really research. It's things going on in laboratories that physicists are working on to try to invent new computers. Quantum computing is one method we're exploring.
그러면 무엇으로 다음에는 어떤 컴퓨팅 기술이 있을까요? 한 가지 가능성은 물리학자들이 연구하고 있는 퀀텀 컴퓨팅입니다.
Quantum computers work in an entirely different way. Conventional binary computers, a bit is 1 or 0. In a quantum machine, a qubit, the equivalent, can be probabilistically somewhere between 1 and 0.
그러나 퀀텀 컴퓨터는 기존의 컴퓨터와 완전히 다른 방식으로 동작합니다. 기존의 컴퓨터가 비트 0과 1 값을 사용한다면 퀀텀 컴퓨터는 큐빗 0과 1 사이의 확률적인 값을 사용합니다.
That gives it incredible computing capability, together with a thing called quantum entanglement. Those two things together enable us to do some computations, not all, dramatically faster.
이러한 큐빗과 양자 세계의 특징인 퀀텀 인탱글먼트를 활용해서 강력한 컴퓨팅 파워를 구현해낼 가능성이 있습니다. 그런데 문제는 이것이 일반적 컴퓨팅 파워가 아니라 아주 특수한 목적에만 빨라지는 컴퓨터라는 점입니다. 미래 퀀텀 컴퓨팅의 가능성에 긍정적인 견해도 있고 부정적 견해도 있습니다. 둘 다 살펴보도록 하겠습니다.
Quantum computers use the natural world to produce machines with staggeringly powerful processing potential.
I think it's going to be the most important computing technology of this century, which we are really just about 1/5 into.
IBM 부사장은 퀀텀 컴퓨팅이 21세기의 가장 중요한 기술이고 우리는 이제 막 그것을 시작했다고 이야기합니다.
We could use quantum computers to simulate molecules to build new drugs and new materials.
몰레큘, 분자를 시뮬레이션해서 새로운 드럭, 약이나 머티리얼, 물질을 만드는데 활용합니다.
And to solve problems plaguing physicists for decades.
수십 년간 물리학자들을 괴롭혀온 문제들을 푸는데도 사용합니다.
Wall Street could use them to optimize portfolios, simulate economic forecasts, and for complex risk analysis.
월스트리트 같은 금융 분야에서는 주식 포트폴리오를 옵티마이즈하고 경제 전망을 예측하고 복잡한 리스크 분석하는 데 활용하도록 합니다.
Quantum computing could also help scientists speed up discoveries in adjacent fields like machine learning and artificial intelligence.
머신러닝과 인공지능 연구를 스피드업하는 데 도움을 줍니다.
Amazon, Google, IBM, and Microsoft, plus a host of smaller companies such as Rigetti and D-Wave, are all betting big on quantum.
아마존, 구글, 마이크로소프트, 리게리, 디웨이브 같은 기업들이 모두 퀀텀에 크게 모험을 걸고 있습니다. 지금까지의 내용을 보면 퀀텀 컴퓨팅은 21세기의 가장 중요한 기술 중에 하나처럼 보일 수도 있습니다. 그러나 그 반대 의견도 존재합니다. CNBC는 퀀텀 컴퓨팅이 왜 절대로 성공하지 못할 것인가에 대한 리포트를 만들었습니다. 어떤 학생들에게는 내용이 아주 흥미로울 수도 있고 어떤 학생들에게는 내용이 너무 어려울 수도 있습니다. 따라서 이번 자시는 여기까지만 시청하셔도 출석이 인정됩니다. 동영상 학습 과제입니다. 이번에도 1주차처럼 자유롭게 주제를 잡아서 수행하시면 됩니다. 자, 그럼 어펜딕스로 하이프 오버 퀀텀 컴퓨터를 보시도록 하겠습니다.
Nothing is ever a sure thing, and dealing with the quirky nature of quantum physics creates some big hurdles for this nascent technology.
From the very beginning, it was understood that building a useful quantum computer was going to be a staggeringly hard engineering problem, if it was even possible at all. Right? And there were even distinguished physicists in the 90s who said this will never work.
Is quantum truly the next big thing in computing? Or is it destined to become something more like nuclear fusion, destined to always be the technology of the future, never the present? In October 2019, Google made a big announcement. Google said it had achieved quantum supremacy. That's the moment when quantum computers can beat out the world's most powerful supercomputers for certain tasks.
They've demonstrated with the quantum computer that it can perform a computation in seconds what would take the world's fastest supercomputer years, thousands of years, to do that same calculation. And in the field, this is known as quantum supremacy, and it's a really important milestone.
Google used a 53-qubit processor named Sycamore to complete the computation, a completely arbitrary mathematical problem with no real-world application. The Google quantum computer spit out an answer in about 200 seconds. It would have taken the world's fastest computer around 10,000 years to come up with a solution, according to Google scientists. With that, Google claimed it had won the race to quantum supremacy. But IBM had an issue with the findings. Yes. IBM, the storied tech company that helped usher in giant mainframes and personal computing, it's a major player in quantum computing. IBM said one of its massive supercomputer networks, this one at the Oak Ridge National Laboratories in Tennessee, could simulate a quantum computer and theoretically solve the same problem in a matter of days, not the 10,000 years that Google had claimed. Either way, it was a huge milestone for quantum computers, and Silicon Valley is taking notice. Venture capital investors are pouring hundreds of millions of dollars into quantum computing startups, even though practical applications are years or even decades away. By 2019, private investors have backed at least 52 quantum technology companies around the world since 2012, according to an analysis by Nature. Many of them were spun out of research teams at universities. In 2017 and 2018, companies received at least $450 million in private funding, more than 4 times the funding from the previous 2 years. That's nowhere near the amount of funding going into a field like artificial intelligence. About $9.3 billion worth of venture capital money poured into AI firms in 2018. But the growth in quantum computing funding is happening quickly for an industry without a real application yet.
It is not easy to figure out how to actually use a quantum computer to do something useful, right? So nature gives you this very, very bizarre hammer in the form of this interference effect among all of these amplitudes, right? And it's up to us as quantum computer scientists to figure out what nails that hammer can hit.
That's leading to some backlash against the hype and concern that quantum computing could soon become a bubble and then dry up just as fast if progress stalls. Quantum computers are also notoriously fickle. They need tightly controlled environments to operate in. Changes in nearby temperatures and electromagnetic waves can cause them to mess up. And then there's the temperature of the quantum chips themselves. They need to be kept at temperatures colder than interstellar space, close to absolute zero. One of the central tenets of quantum physics is called superposition. That means a subatomic particle, like an electron, can exist in two different states at the same time. It was, and still is, super hard for normal computers to simulate quantum mechanics because of superposition.
Now, it was only in the early 80s that a few physicists, such as Richard Feynman, had the amazing suggestion that if nature is giving us that computational lemon, well, why not make it into lemonade?
You've probably heard or read this explanation of how a quantum computer works. Regular or classical computers run on bits. Bits can either be a 1 or a 0. Quantum computers, on the other hand, run on quantum bits, or qubits. Qubits can be either 1 or 0, or both, or a combination of the two at the same time. That's not wrong per se, but it only scratches the surface according to Scott Aronson, who teaches computer science and quantum computing at the University of Texas in Austin. We asked him to explain how quantum computing actually works.
Well, let me start with this. You never hear your weather forecaster say, well, there's a negative 30% chance of rain tomorrow, right? That would just be nonsense, right? The chance of something happening is always between 0% and 100%. Okay, but now quantum mechanics is based on numbers called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers involving the square root of -1. So a qubit is a bit that has an amplitude for being 0 and another amplitude for being 1.
The goal for quantum computers is to make sure the amplitudes leading to wrong answers cancel each other out, and that scientists reading the output of the quantum computers are left with amplitudes leading to the right answer of whatever problem they're trying to solve. So, what does a quantum computer look like in the real world? The quantum computers developed by companies such as Google, IBM, and Rigetti were all made using a process called superconducting.
Okay, and this is where you have a chip the size of an ordinary computer chip, and you have little coils of wire in the chip, which are actually quite enormous by the standards of qubits. They're nearly big enough to see with the naked eye. Okay, but you can have two different quantum states of current that are flowing through these coils that correspond to a 0 or a 1. And of course, you can also have superpositions of the two. Now, the coil can interact with each other via something called Josephson junctions. Okay, so they're laid out in roughly a rectangular array, and the nearby ones can talk to each other and thereby generate these very complicated states, what we call entangled states, which is one of the essentials of quantum computing. And the way that the qubits interact with each other is fully programmable. Okay, so you can send electrical signals to the chip to say which qubits should interact with each other ones at which time. Now, in order for this to work, the whole chip is placed in a dilution refrigerator that's the size of a closet, roughly, and that cools it to about 1/100 of a degree above absolute zero. That's where you get the superconductivity that allows these bits to briefly behave as qubits.
At IBM's research lab in Yorktown Heights, New York, the big tech company houses several quantum computers already hooked up to the cloud. Corporate clients such as Goldman Sachs and JP Morgan are part of IBM's Q network, where they can experiment with the quantum machines and their programming language. So far, it's a way for companies to get used to quantum computing rather than make money from it. Quantum computers need exponentially more qubits before they start doing anything useful. IBM recently unveiled a 53-qubit computer, the same size as Google's Sycamore processor.
We think we're actually going to need tens of thousands, hundreds of thousands of qubits to get to real business problems. So you can see we need quite a lot of advances, and doubling every year, or perhaps even a little faster, is what we need to get us there. That's why it's 10 years out, at least.
Quantum computing would need to see some big advances between then and now, bigger advances than what occurred during the timeline of classical computing and Moore's Law.
Oh, we need better than Moore's Law. Moore's Law was doubling every 2 years. We're talking doubling every year, with occasionally some really big jumps.
So once quantum computers become useful, what can they do? Scientists first came up with the idea for quantum computers as a way to better simulate quantum mechanics. That's still the main purpose for them, and it also holds the most money-making potential.
So one example is the caffeine molecule. Now, if you're like me, you've probably ingested billions or trillions of caffeine molecules so far today. Now, if computers are really that good, right, really that powerful, and we have these tremendous supercomputers that are out there, we should be able to really take a molecule and represent it exactly in a computer. And this would be great for many fields: healthcare, pharmaceuticals, creating new materials, creating new flavorings, right? Anywhere where molecules are in play. So if we just start with this basic idea of caffeine, it turns out it's absolutely impossible to represent one simple little caffeine molecule in a classical computer, because the amount of information you would need to represent it, the number of zeros and ones you would need, is around 10 to the 48th. The number of atoms on the Earth are about 10 to 100 times that number. So in the worst case, one caffeine molecule could use 10% of all the atoms in the Earth, just for storage. That's never going to happen. However, if we have a quantum computer with 160 qubits, and this is a model of a 50-qubit machine behind me, you can kind of figure, well, if we make good progress, eventually we'll get up to 160 good qubits. It looks like we'll be able to do something with caffeine on a quantum computer, and it's never going to be possible on a classical computer.
Another potential use comes from Wall Street: complex risk analysis and economic forecasting. Quantum computing also has big potential for portfolio optimization. Perhaps the biggest business opportunity out of quantum computing in the short term is simply preparing for the widespread use of them. Companies and governments are already attempting to quantum-proof their most sensitive data and secrets. In 1994, a scientist at Bell Labs named Peter Shor came up with an algorithm that proved quantum computers could factor huge numbers much more quickly than their classical counterparts. That also means quantum computers, if powerful and efficient enough, could theoretically break RSA encryption. RSA is the type of encryption that underpins the entire internet. Quantum computers, the way they're built now, would need millions of qubits to crack RSA cryptography. But that milestone could be 20 or 30 years away, and governments and companies are beginning to get ready for it.
You know, for a lot of people that doesn't matter. But for example, for health records, if health records could be opened up, that could compromise all kinds of things: government communications, banking records, sometimes even banking records from decades ago contain important information that you don't want exposed. So the problem we've got is we don't really know when quantum computers will be able to do this, or even if we'll ever build one big enough to do this. But what we do know is if you don't update your cryptography now, all the messages that you send over the next few years, the ones in history, could potentially be read. What this means is, for example, if you're a Cisco selling networking equipment, you're going to need to offer quantum-safe encryption as an option in the very near future, because even though it doesn't look like we need it right away, if your product doesn't have it and a competitor does, guess which product gets bought?
One big issue facing quantum computing, other than increasing the number of qubits while keeping things stable, is that no one actually knows the best way to build a quantum computer yet. The quantum computers that Google and IBM and other companies show off are very much still experiments. There's also a big education gap. Not many people are studying quantum computing yet. China is pouring billions into quantum computing education, and the U.S. Congress passed a law in 2018 called the National Quantum Initiative Act in order to help catch up.
Quantum computing capable people will be a rare commodity, which means that you want to invest in them now. You want to be hiring people with quantum computing knowledge, not necessarily to do quantum computing, but because you want that intelligence in your organization so that you can take advantage of it when it shows up. Now, China, with its promise to put $10 billion in, is really upping the stakes in terms of the number of Chinese quantum physics PhDs that are going to start appearing. And you know, if that hair restoration or life extension drug happens to be property of the Chinese government, what does that do to the world economy? That's much more powerful than making war.
Other experts have compared Google's announcement to Sputnik, the Soviet satellite launched into orbit in 1957. The beach ball-sized satellite was the first man-made object to orbit the Earth. But Sputnik didn't really do anything useful, other than prove launching something into space was possible.
Many people are surprised that where exactly we are. For those who are just getting started, they like to make noise about vacuum tubes and Sputnik and things like this. But let me give you some numbers. IBM has had quantum computers on the cloud for 3.5 years, since May of 2016. We're not in any sort of Sputnik era. We're not landing on the moon. But for those of you who like space history, I think we're probably well into Mercury or Gemini.